Yeah. Am I audible?
Yes. I'll introduce. Okay, it's my pleasure to introduce Madhusudhan Reddy Pittu. And he is a student at CMU. And prior to that, he did BTech from IIT Kharagpur. He was an intern here, another intern at IISc. He's also an IMO bronze medal recipient. Nowadays, he is working on approximation algorithms and other cool topics. Probably we'll talk about them. So today he'll talk about efficient determinant maximization for all Matroids.
Thank you, Arindam, for the very nice introduction. I'm very grateful to Arindam because he is the one who introduced me to this. So yeah, today we'll discuss about efficient determinant maximization for all Matroids. So I'll define what Matroids are. Even like I'll assume you don't know anything about Matroids, and I try to make this talk as complete as I can. Yeah. So yeah, this is joint work with Adam Rowan, Alti Labda, Mohit Singh, and Prasad Tatwani. So yeah, let's get straight to the problem. What's determinant maximization? Let's say you're given a bunch of vectors v1 up to vn, all of them d-dimensional. So say they look like this. You need to select a subset of them so that you maximize this determinant of sum of outer products. It looks very artificial at first, but once we look at applications, it will be clear why it's important. And as of now, there's no problem at all because this monotone, right? I can just select all of them. But yeah, you have certain combinatorial constraints on the set. Either it can be a cardinality constraint, which means you can pick only a constant size, or it can be a partition constraint, which means if I color the elements, you need to pick, like, say, one in each or a constant number from each bucket, right? So more generally, you can generalize these two constraints as being a basis of a matroid. Yeah, we'll get to what matroid and basis are, but till then you can just think of these two cases. Okay, so observe that if k is less than d, if you're picking less than d vectors, then the matrix inside is already low rank and the value is 0. So in that case, it makes sense to think of the objective as the product of top k eigenvalues, right? Or yeah. So let's say Vs is the matrix that has vectors indexed by the set as columns. So yeah, when k is less than d, it's okay. So as of now, the objective is Vs transpose, but if k is less than d, you can think of the object as Vs transpose v, because product of top k eigenvalues will be the determinant of the inner product matrix by similarity. So what's the first application? It's experimental design. Let's say you have an unknown theta, which you want to find out. It's d-dimensional. And then you're trying to design, before just trying and find theta, you're trying to design an experiment that will let you know what theta is. So what do I mean by that? You have a bunch of vectors v1 up to vn, and you can only pick a few subset of them so that you'll get these linear measurements of theta star with some noise, right? And yeah, feasible set of measurements are some subset of k, and it can be any subset of k, but more generally, we want it to be combinatorial, like it has to be a basis of a matroid. But yeah, and what's the goal? I want to choose that subset of vectors that will give me the most accurate estimate. And what do I mean by that? Once you have a bunch of vectors, The obvious estimate is the maximum likelihood estimate, which you get by minimizing this squares error. And it's known that theta hat minus the actual theta star is distributed as this multivariate Gaussian with the following coherence matrix. So if you look at the confidence ellipsoid, so which is this object, so you can guarantee that the actual theta star is within in this ellipsoid with 95% probability. So what you want is so the notion of accuracy here is the volume of this ball. You want to make this ball as small as you can. So that's equivalent to minimizing the volume of the ellipsoid is equivalent to maximizing the following determinant. So, and you can have other notions of accuracy. You can say I want to minimize the average variance, and that's the trace, and then you want to minimize the width of this ellipsoid, which is the length of the longest major axis. So that will be minimizing the operator now. So yeah, so that's one application.
So the volume is not taking the to the.
Oh yeah, right. When I tend to use volume and determinant interchangeably, but one is a square of the other. Right. Yeah. Another application is Nash social welfare. So the setting is where you have indivisible goods and B agents, and agent I has utility Uij, and the total happiness of agent I is additive. Say these two are the agents and these three are the items, and you also have constraints on whether you can't give any object to anyone. Since Morty is just 14 years old, he can't have the first object. So and then they have so these are the valuations. So the object is to find an allocation so that you maximize welfare. So what's the notion of welfare here is the geometric mean of the happinesses of all the people, right? And you want to maximize that. So the claim is this is the special case of determinant maximization under partition constraints. So yeah, let's see why. So let's create a bucket of vectors for each object. And here's how I'm going to encode an instance of Nash social welfare. So basically, the partition constraint here is that each object can only go to one prime. So for every possible allocation of an object j to agent I, I'll put a vector in the bucket corresponding to the object. So what I'm doing is, for every allocation, there is a corresponding choice of vectors. And once you take the outer product and add them all up, so each coordinate corresponds to an agent. So the first coordinate is Rick here and the second coordinate is Morty. And I choose a vector smartly so that once I take the outer product and add the sum, the first coordinate will have the total utility of the first agent, and the second, it will be a diagonal matrix because as you see the vectors I'm choosing only have one non-zero entry. And yeah, you can see that I chose the valuations to be perfect squares so that once I take VB transpose, so that V can be nice integer vector. But yeah, you can see that each allocation is basically picking one vector from each bucket. So which vector you pick will encode who the object goes to, and the objective is clearly so the determinant is just a product of the utilities. So yeah, the 1/d doesn't the geometric mean doesn't matter. You can just consider the product, and there's a clear mapping of allocation and objective value. Nice. So yeah, is this reduction clear? Right. I didn't want to explicitly write down if like I just want to leave it at here like. So, and this problem is well studied, and there's an approximation by Anari Shainaves, Mohit, and oh yeah, the E approximation is for determinant maximization and partition constraints, and that also gives E for this problem. And just for natural welfare, you have 2e to the 1 by a by Cole, and Burman had finding fair and efficient allocations. So that gives this e to the 1 by e approximation. That's the best right now, as to my knowledge. And this is APX hard. Network design.
What is the lower bound?
1.0008 by E Wong Lee. Oh, I didn't know. Thanks.
1.1.
Yeah. So this application network design as well. So given a graph, I want to find a spanning subgraph. So I can only pick a subset of edges, but it is spanning, and it has to be well connected. And you can't pick any subset of edges. They have to satisfy certain combinatorial constraints. So we'll define what well connected means and what combinatorial constraints are. So one obvious combinatorial constraint is the cardinality at most scale. Or I mean, every time I just give a cardinality or a partition matroid constraint, so you can you can pick one edge from each color class. So that's basically a partition matroid constraint. And one studied notion of well connected is maximizing the number of spanning trees in it. Not disjoint, yeah, just counting the total number of spanning trees in it. So this problem is an instance of like this can be reduced to determinant maximization, because each edge you can consider vector, like yeah, whether choosing an edge is choosing a vector, and from Kirchhoff theorem we have that the number of spanning trees is determinant of this sum of outer products of these vectors. So as you can see, it's yeah, you're just choosing edges is choosing vectors, and you're trying to maximize this. So it's and what vectors you can pick is you have a combinatorial constraint on that. So it's yeah, determinant maximization with matroid constraints. This is subcase of that, right?
AP is equal to
Oh, I see. It's a type. Yeah, sorry about that. Right. Okay. And convex geometry. So this one you're given n vectors in R to the D, and I want to pick D of them so that I maximize the volume of the parallel pipe. So and yeah, volume is a square root of this PS transpose Vs. Right, and this has been studied by Kache, and he gave a D to the D greedy algorithm that gives a D to the D approximation. It's been improved to E to the D by Nicola using convex programming and stable polynomials. I remember this randomized rounding, but yeah, I think it's deterministic. Yeah. Okay. So yeah, I hope it convinced you well enough that this problem generalizes a lot of problems. So what's the previous work done on this? So this problem is easier when the matroid is uniform. So uniform matroid is when you just have a cardinality constraint, right? So yeah, the same Nicola's work gives e to the D approximation, and there are volume sampling methods that give very good approximation. So you see that these approximations are exponential. That's because determinant is this d-dimensional quantity. So you can think of the objective as determinant to the 1 by d, then these will be constants as in natural welfare. So yeah, so k is the rank of the matroid, and if I'm allowed to pick much more than dimension, then you get very good approximation. And all these methods have to solve some sort of convex program, and those are in general very heavy. Local search is pretty light. You just need to do an exchange and compute the value of the new solution, right? So
These are all the reals, like determinant.
oh yeah. Yeah, I'm not aware of these generalizations. I'll get back to you.
For small k, what is the volume family? K less than equal.
I'm not sure. As from what I know, it gets easier if k is larger. So I don't think the same result holds, but I'm not sure. Yeah. So this local search and greedy that works when k is again large, and for general matroids, there's this literature of real stable polynomials, strongly log concave polynomials, and you write a convex program and then oh, can you hear me? Yeah, sorry about that. So I'll just try to talk to you. Yeah. Yeah.
Mind if I keep the battery? Keep telling you
But I can speak like this.
don't have to, like, try to pin it up. If not,
Am I audible?
yes.
Yeah, cool. Yeah. So yeah, well, using convex programming and the literature strongly real stable polynomials, we can get a e to the d approximate estimation. So what that means is I'll solve a convex program and I'll get a fraction solution, and the value of that will approximate the actual value, but I'll not get a solution. If you need to get a solution, then you need to incur more loss. So you can keep solving, and then to get an actual solution, you need to solve this many times, and then you have this the e to the d happens d times, and then it multiplies, and you get this e to the d square. And this is when k is less than or equal to d. And for k greater than d, use convex programming, and you get a d to the d approximate estimation and d to the d square approximation. So as you can see, these are all very bad guarantees with a lot of heavy computation. So combinatorial methods are in general, yeah, as I said, they are light. So we came up with, as of now, we have a d to the d approximation when k is more than d, and k to the k when k is less than. Even here, I guess this e to the d and e to the d square are when k is d, but they become e to the k, and I'm not sure if it's k square or kd, but yeah, at least yeah, this e to the d is e to the k. But yeah, so I'll try to spend more time giving you details of what's happening and make it more complete and as simple as I can.
So what was the E approximation? What was that? 1 over dx power.
Oh, you mean for Nash social welfare?
Right.
Yeah, that's because there is a 1 by d in the objective.
Oh, okay.
I'm taking the geometric mean. We can do that here as well, but yeah. Then all these d's in exponents will go off. But yeah. So one observation is, let's say I don't want to forget about maximizing the determinant. Just give me a solution that has non-zero value. Let's even imagine k is d. So you need to pick. So all vectors are d-dimensional. There are n of them. You need to pick d of them, and you need to tell. And the set you have to pick is has to be a basis of a matroid, and just tell me if the solution there is a non-zero solution. That's a clear case of Matroid intersection, right? Between the linear Matroid and the constraint, right? So clearly, it yeah, makes sense to try and do something with Matroid intersection where you have to kind of quantify Matroid intersection, not just finding a common basis, but the basis should have a very good value with respect to this objective value, right? So we'll just quickly brush up these Matroid results. So Matroid is this set system where it has this downward monotone property, which means so it's a collection of subsets, and if one subset is there, then all its subsets are also there. And if there are two sets and one is larger, then there exists an element that I can give from B to A. Right. Sorry, A to B. A is larger here, right? And what's a basis is the maximal inclusion-wise maximal independent set, and just from these two properties, you can say that all bases have the same size. Yeah. So yeah, think of spanning trees, right? They are always of the edges are the elements and the bases are the spanning trees, and they always have the same size. Yeah. If you give me two Matroids, and if a set S is in both the, so these I's are called independents. So if a set S is in I, then it's called independent in that Matroid. So if a set S is in both I1 and I2, then it's said to be in the intersection of these two Matroids. And very famous theorem is that maximum weight common basis can be found in polynomial type. So maximum matching is an instance of a Matroid intersection. Just it's an intersection of two partition Matroids. You're picking one edge incident on each vertex on both sides. So that's partition Matroids on both sides. Right, yeah. So, and the Matroid intersection algorithm itself looks like it's just generalized version of the actual max matching algorithm. So setting up the framework. So what's an exchange graph? So given a Matroid and an independent set, you have the following exchange graph, which simply encodes what local exchanges I can make and still stay an independent set. So x and y have an edge if s minus y plus x is still an independent set. And the two most important structural lemmas that we just use these two, and all the results in weighted like in weighted max weight intersection, we just keep using these two lemmas to show that we're already at the optimal solution, or you can move from one solution to a better solution. So yeah, what's the first lemma? If you have two independent sets of the same size, then there is a perfect matching on the symmetric difference of this. You can try to prove that. It's a nice exercise. And the second, it's a counterpart which kind of gives the other side. If I know that S is an independent set, but I don't know that if S dash, which is of the same size, is not an independent set, but I see that there's a unique matching between in the symmetric difference, then I can guarantee that S dash has to be independent. I'll give it a minute for you to just.
Yeah, right now focusing on a single, like typically exchange graphs are defined with two matroids, like for the matroid intersection, but here you're focusing on a single matroid.
Oh yeah, so the exchange graph that we have for two matroids is just the union of two of these. So the next slide, from the next slide, we have that. Right. So the exchange graph given. Okay, maybe I shouldn't have called this exchange graph, but yeah, that's yeah. Given two matroids and one common independent set, so S is already in I1 and I2. The exchange graph basically encodes. It's just a union of both the previous graphs where you just direct the edges from one graph forward and the other backward. Yeah. So now let's think about the following problem. Say the elements are weights, and I define weight of a set to be just sum of the weights. And right now S has a certain weight. How can I check if S is the maximum weight common basis? I'll also yeah. Let's say S is a common basis, and yeah, it has certain weights. Now, how can I certify or check that S is the maximum weight common basis? Right. So let's just put weight Wx minus Wy on only the forward edges, and let's just put weight 0 on the backward edge. Right. So using the first lemma, if you remember, yeah, there is a perfect matching. Yeah. So okay, what I'm doing here is, let's say there is a set S dash, another common basis S dash that has larger weight than S. Then let's just imagine it, and then we know that there's a forward matching, and the total weight of that matching is just the difference of weights of S dash and S, just because the weights were just Wx minus W. Right. So if S dash is of higher weight, then this is positive. And we know that there is a backward matching as well, just because S dash is an independent, S and S dash are independent sets in the second matrix, I1 as well, M1 as well. Right. And if you just take the union of this, they decompose into cycles. And if better S dash exists, then since the total weight of all the cycles is the weight of the matching, since we just put weight on red edges, we will observe a positive cycle. And it's easy to detect a positive cycle, right? You just maybe just invert the weights and then run a negative cycle detection. Right. So if no positive cycle exists, then we know that we are at the maximum solution. So that's like a certificate. I am at the maximum weight common basis. Now the next question is, sure, but do I know that if I am already do I have the other direction? So if there is a positive cycle, that does that imply that there is a better S dash? Turns out yes. So why just pick the minimum hop positive cycle, and I'll show that exchanging on that. Basically, if you exchange on the set of elements on the other side with S, then you'll remain an independent set in both Matroids. So if you exchange on any positive cycle, you don't. The problem is staying independent in both Matroids. We'll see why this minimum hop is crucial. Really, it's because of the second lemma where you have this unique perfect matching instead of perfect matching. So
when you say minimum hop positive cycle among all
positive cycles, look at the one with the least number of vertices. Right. So I'm just
all cycles will be alternate edges by construction.
Yeah. Right. So let's say this is the, so let's just imagine this is already the that minimum hop positive cycle, and I just need to prove that S dash is an independent set in both Matroids. How is that? Suppose not. If S dash is not an independent set, suppose in the first Matroid I1, then by contrapositive you need to have another match. So if the blue matching is unique, then you know that S dash is an independent set in the first Matroid. So there has to be this other, there should be another blue matching. So I can just use edges from the blue matching to break the cycle into smaller cycles. And since all the red, so yeah, basically the sum of weights of these cycles is the weight of the original cycle. Since it's positive, one of these have to be positive, and that connotates the minimum hop positive cycle. assumption. So that implies that there is only the blue matching has to be unique. So S dash is independent in I1 at least. So how do I prove that it's unique in the red matching is also unique in? Yeah, how do I prove that the red matching is unique? Say it's not again, and say you have two other red edges, then you also break into two new cycles. But yeah, you can still say that the sum of the weights of these two cycles is the weight of the original cycle, because in this figure the sum of weights of these two red edges A dash A and C dash C is the same as the sum of weights of A C dash and A dash C, just because 1 minus 2 plus 3 minus 4 is 1 minus 4 plus 3 minus 2. So yeah, that shows that these matchings have to be unique in both directions. So S dash is an independent set in both matroids. So yeah.
Show me the second lemma again.
Next one. I went too far. Right. So if I look at this valued exchanges, it should have a unique match.
In the intersection thing, it should have unique matching for both the red and blue.
Yeah, the forward and back, and that we get with this minimum half cycles. Right. So that's matroid intersection, like a small part of matroid intersection. But so what if the weight of a set is just, has product structure instead of sum? We can just take the logarithm and it's the same problem. What if it's determinant, which is the volume of, since I'm picking d-dimensional vectors, it's also the volume. Well, there can be magnitude difference, but I guess I should have mod that instead of that. But yeah, so why I mentioned W of S is product of W is determinant can have. So what if all the vectors are orthogonal somehow? Any S vectors are orthogonal, which is not possible, but if that magically happens, then it's just it has product structure, right? So determinant is a very multiplicative. I mean, it's multiplication of eigenvalues, so it's a very multiplicative. It's a product object. So the motivation is that let's set the so now we're precisely taking log volume and then just doing the same thing we have done before. Wx minus Wy. Wx minus Wy is just W of S minus Y plus X minus is the new weight of the set after exchanging minus weight of the old set, right? So that's what we're doing. How is the object log volume changing with a swap? So those are our weights. So now I'll ask the same question. How can I certify that S is a d to the order d approximate max weight common basis? Previously, I was just asking how do I know that it's optimal? Now I'll say, how do you know it's d to the d approximate? Because of course there's a loss because volume is not it doesn't have this multiplicative subset.
Cycle with this factor loss. That's a certificate. Right? So with these weights, there is no cycle. With the total weight more than d to the d times the current.
Right. Yeah. So yeah. So basically, that's what happens. That's what I'm about to say. So suppose there is again I'm going to repeat the same kind of argument. Suppose there is an S dash so that the volume is so and so large, more than volume of S. Then let's just represent the elements in S dash in since the size of S is d, it spans the space. All other vectors I can write in terms of these vectors. So let Vs dash be Vs times A transpose, which means Vx is sum of Ax, y, Vy. So yeah, so the ratio of volumes is just the determinant of this transformation matrix. And since yeah, some of these elements can be common, the determinant I can also write as the determinant of just, so A is a matrix that the rows of A corresponds to elements in S dash, and columns of A corresponds to rows in S. So anyway, so what is this log volume S minus y plus x by volume of x? It's just log AXY, right? Because yeah, the new vector Vx that you're adding, what matters is it's when you break it down, what is its how much is the scaling Vy, because the rest gets cancelled out, right? Oh. So then this determinant, if you open up as okay, sorry, I ignored the sign, but we just take this modulus and then upper bound it with, yeah, we ignore the sign anyway. We just, so if the determinant is large, in essence, if the determinant is large, there is a matching with high weight. This just by taking this out of all the d factorial or l factorial matchings, we are just taking one of them. So d to the order d still remains d to the order d. So basically, if the gap is so large, then one of the matchings has a lot of weight. And once that happens, I'll take union with the other matching, and then they decompose into cycles. And since L log L grows more than linearly, one of the cycle has to be of size C log C, if C is the number of vertices in a cycle. So, and if no such a cycle exists, then that's a certificate that you're already D to the D approximation. So we're really trying to, yeah, we really followed the same approach, where if some set is more than that, then there's a positive matching, and there's a positive cycle, and the same stuff that's happening. And now the question is, what about the other direction? So what do I do if I find a large weight cycle? Same, I exchange a min hop large weight. So the notion of large here is a cycle is large if the weight on it is more than C log C, order C log C, right? And yeah, first let's prove that after exchanging with such a cycle, at least S delta C stays in I1. Why is that? If not, if there is a different blue matching, then again I'll break the cycle into more cycles, and since the weights are only on the red edges, the total weight is more than C log C, and one of the, like, yeah, again since x log x grows faster than linearly, one of the smaller cycles should be large as well. So since we already picked the minimal large cycle, this should not happen. So at least I know that when I exchange with other cycle, S dash is independent.
Is it both positive and negative weights on the cycle?
Yeah.
How you find the minimum of large weight cycle?
I see, right. How do I find if a cycle has more than C log C? So that,
You do want an efficient
yeah, we can find it, because let's say I start with trying to see if there is a size 2 large cycle, then size 3 large cycle. Okay, when I'm trying to find a size 2 large cycle, I invert all the weights and add C log C, 2 log 2, order 2 log, and I see if there's a negative cycle. And if I don't find one, then that should find a negative cycle. In fact, it will find the minimum of negative cycle if I keep doing this. Right. Yeah, now we just need to argue that once I exchange on such a cycle, the volume increases by more than 1 plus alpha for some constant. Equivalently, that means that I want to show that this determinant, the magnitude of this is more than 1 plus alpha. And the idea of that is basically again saying, oh, this is the min hop large cycle. So if I look at any red shortcut, this smaller cycle wasn't large. So that gives an upper bound on, like, you get this, you get the weight of C dash B and sum of weight of C dash B and sum of weight of H A dash A is less than, I'm just calling the function G. And for all these shortcuts, you get this. So basically what's happening is we're looking at the determinant matrix, and in some sense we're just providing upper bounds for the non-diagonal entries, and there's a lower bound for the product of the diagonal. That will in some sense just give you a lower bound on the determinant. So basically you should imagine this like yeah, you're trying to show that all the off diagonal entries are small. Not exactly, but if you just open up the determinant, the diagonal is what dominates. All other permutations, they don't compare with the diagonal. So the determinant is approximately just the product of the diagonal entries, which we know is large. Right. So I mean that's the algorithm for case D. We just do this. We just define this notion of large cycle. We just set up the same exchange graph, and we just put this log new volume by old volume, and then you just check if there's a large cycle, and then you just exchange on the minimum hop large cycle, and you're guaranteed to stay in the independent set, constraint in the Matroid, and your objective value in the linear Matroid will increase. So if you just keep doing that, you'll reach the optimum in linear number of iterations. Linear in the encoding size of the problem. Yeah. So just putting pieces together, you start with the common basis of both the linear and constraint Matroid, and you set up the exchange graph. And while there is a large cycle, you just find a min hop large cycle, which you can do using it. You can just reduce that problem to finding a negative cycle in the same graph with different weights, and you just yeah. So a cycle is large if the number of vertices is, let's say, C in that cycle, then the weight has to be more than order C log C. The constants we choose carefully so that everything works out, but that's basically the idea. And as you can see, just generalizes the previous idea, where how do you know that you are a good solution? And once you have this positive cycle, you know that if you exchange on that minimal positive cycle, you will stay independent and the value increases. It's the same idea that we're doing, but since there are losses because of that approximation, we just consider weights as log new volume by old volume, so there are losses. But now and so that gives this D to the order D approximation. And you can ask, how bad can the gap between optimal and, can the algorithm really do D to the D bad? And the answer is yes. If the optimal vectors are situated in the Hadamard position and your solution is the standard basis, then any exchange does not change the volume. If I throw away any standard basis and add in any Hadamard vector, the volume stays 1. So in the exchange graph, all these weights are zeros, log new volume by old volume. So you won't detect any cycle at all. and the gap between the volumes is d to the d by 2. So it can, yeah, till this gap, the algorithm won't see any large cycle, but slowly as a constant in the C, d to the CD, when C is around 5, then we can really say, oh, we are really bad. We can improve. So yeah, in that sense, it's kind of tight. So
one question. Yes. Linear method, constant method you choose. But if I don't like what objects will come, there is some other Matroids there. So arbitrary Matroids M1 and M2 they choose and run the algorithm. Might solve some other problem, it's a determinant maximization, or do you see any other application of the same algorithm, just the Matroids equivalent?
So are you saying let's so it's the same problem. I'm given 2 Matroids and I'm trying to maximize some other set function while staying in the basis. We don't know. We're trying to find out what functions does this work well. So clearly, this volume function seems to work well, but it's not clear what kind of functions we can approximate using this method.
Lower bound of DPP or it's typical for any exchange argument you will not win, but maybe some other algorithm could be there which is not using.
Yeah, I mean, this is just like the hard instance, or it can do terribly bad in this. Our algorithm will do terribly bad.
But this particular instance, any other algorithm, like other algorithms which can be just for, or maybe there is for this particular. What I'm saying, combination of multiple algorithms, do you see?
It's not. Yeah, I mean, I understand what you're saying. Okay, so such hard instances, maybe you can solve easily using some other algorithm. So if you just combine 2 different methods, maybe you can beat this d to the d and get to maybe e to the constant to the d. We don't know.
Properties of this volume. Trying to understand what is it that you actually leverage. It's certainly for the additive functions, the standard Edmonds algorithm works. But now what you're showing is that fine.
So the question is, what really? What did we? So this determinant we use. So really, we use this. We opened up this determinant, took a matching out of it. We just took one permutation, and that is a matching. Basically, if we can guarantee a good weight matching, that's what's happening, right?
My mind is following that there is a good enough linear approximation to your function. That it is log weights, right? This is exactly like saying you look at the marginal at that current solution, and yeah, you just look at the sum of the marginals. And somehow you're saying that was a good enough surrogate for the overarching function. So your D of S is exactly determinant of capital for any subset that you pick. It's just
the volume of the vectors corresponding to that. One thing we know is log volume is submodel.
Is it?
Yeah.
Log volume is submodel. So, does this generalize the same that I can optimize, approximately maximize submodular functions over Matroids?
That's a question I'm interested in. I kind of want to believe that, but it's not clear if that's true. So what you're saying is any function that's log, any function, if I take the log of that, if it's submodular, which in this case is, if that's
even that, just take a submodular function. W. So instead of W being an additive function,
it's just
submodular. So This has been studied, right?
Oh, this is submodular maximization under Matroid constraints,
Yeah.
Matroid based constraints. We have
Yeah.
constant approximations.
Yeah, so why does that not keep it? Because
So
we are
those
looking at-
weren't combinatorial really. They use this multi.
I mean, there are multilinear extensions.
Yeah, multilinear extension.
Maybe it's the fact that when you exponentiate that, you don't get as good a guarantee or something. That has been studied, like maximizing a submodular function subject to, in fact, intersection of not just two but like K matrix.
P systems, then
Yeah,
there's.
but that is not what is taking it.
I mean, what even is D here, right? With respect to the function, we're giving a D to the D approximation, but what even is D with respect to the volume of? So what property can extract D from by just looking at the volume? That's not.
D is more like the some implicit property. Anyway, okay.
Yeah. So I'm thinking about it, but it's not clear what made it. Can we abstract out this and remove volume and say something else?
But like just to connect it to the continuous world, like if you have a function, the log of which is concave, when it's drawing an analogy. If it's concave, then those are well studied. Those are called X-concave functions. They have, like for example, for regret, yes, very nice like regret there. So they're really like a well-studied class, but in the like, continuous, so it's not set functions, but like convex functions. Okay. Maybe that's just a significant.
Alright, so yeah, that's one question I am wondering as well. What set functions you can maximize using this kind of this framework of arguments. So yeah, and yeah, now what happens if we really crucially use the fact that the size of S was exactly D and all of them are D dimensional? It's that. So yeah, so when you have a new vector that you're trying to exchange with, it can't be written as it need not be in the span of S. It can have some orthogonal component. So yeah, Vx need not will have this perpendicular component. So the ratio of volumes is not simply mod AUV as before. Then you have this other stuff coming in. So we just break this into the way we solve this issue is just break each vector into an orthogonal component and a parallel component. By that, what I mean is parallel to the span of S and orthogonal to the span of S. And just put two edges, and the weights on those are as if you're just exchanging the parallel component or the perpendicular component, and just the same stuff works. If the gap is too much between our solution and another solution, then you will find a large cycle and you can exchange with the minimal large cycle and you can show that the volume grows. And for larger rank, we have to do more work. We need to bring down the ground set size to k plus order d square, and then again it's similar. You just even there you need to put two edges. Yeah, I'll stop there. And key takeaways are that Matroids are awesome. They have very good properties. What we really did here is these two things: determinant to cycle and cycle to determinant. Which are those these two lemmas, right? Lemma A and lemma B. I think those are very important, and it's also fun to try and prove them. Yeah, open problems. Right now it's order D to the D. Can you put constant to the D? Then we'll be kind of done because we have a C to the D hardness. And related problems are these other designs, instead of maximizing determinant, you're trying to minimize trace of the nodes. Maximize the minimum eigenvalue, minimize the maximum. Thanks.
Not lost between these cases, k less than b, k greater than b. Can you remind again?
Yeah, I just wanted to just tell something. I didn't mean to really give the details, but what I mean is, so what, do you have a specific question?
So d is the dimension of the vector, right?
Oh, I'm not sharing the screen. I should share it.
What was k? Just that's the question.
So okay, k is the rank of the matroid. K is the number of vectors you need to pick.
And
So
k is more than d. Right. When k is more than d,
right. Right.
and when k is less than d,
Yeah, think of it as volume. So you can still make sense of volume of so even if there are three vectors and they're all high dimensional, it still makes sense. What volume is makes sense. If there are two, then it's kind of like the area of the parallelogram that they form. So that's really the objective.
If I take determinant of summation bi transpose.
For k less than d, then it's 0.
Right.
Yeah, in that case, when k less than d, the objective is not really the determinant of sum of outer products.
So we switch the
Yeah,
transpose.
yeah, and that's the same thing as product of non-zero eigenvalues or top k eigenvalues.
Yeah, that was the.
And geometrically, that's volume square.
That is a generalization of multiple problems.
Yes.
You do general case, but for the particular special problems, for their particular matrix structure, you get something better here, or you tried that, or
Right. I think this d to the d deterministic approximation that we give, even for partition matroids, that's the best. That's partition. So determinant maximization and partition constraints. E to the d estimation. But if you need a solution, I think you still say e to the d square. So even for partition, so NSW natural welfare is partition constraint and the vectors are all axis parallel. There's even more structure. But just partition constraints doesn't make it very easy. Cardinality constraints makes it easy, but partition is strong.
Like general vectors and partition method gives you the Nash welfare with externalities. So imagine that I look at a Nash welfare problem, but it has, if I give it to you, you get a value and I also get a value. These are called externalities in.
Oh, if you give object, so allocation doesn't mean only one person gets a valuation, but
you're my friend, so if you get a big piece of the cake, I'm also slightly happy.
I see.
Those are called externality. So
then that, yeah, it's precisely that.
So I think the framework actually captures that. Probably the D to the D is, but yeah, it takes the, okay. Interesting.
Yeah, so any more questions?
Have any more questions?
So yours is the only algorithm which is deterministic.
D to the D and deterministic. Yeah, d to the d approximation. So we use approximation to mean deterministic order.
Oh, I thought
So there's a problem with randomized because these objectives are so large, it can happen that in expectation you can be a d to the d approximation, but almost always you get a solution of value 0. Like, yeah.
but they don't give a high probability statement.
Yeah, I don't think so. Yeah. So to deterministically get a good approximation, that's the best.
Appreciation.